Hello students, welcome to the e-learning platform presented by Mechanical Engineering Department of Dr. Bapuji Saloke Institute of Engineering and Technology, Kolhapur. The learning objectives of today's session are: number one, study of different parameters used in bending. The different parameters that are bend force, bend radius, bend allowance, bending length will be studied in today's session. And second, study of bending dies. The different types of bending dies will be studied in today's session. Starting with first point, the bend radius or bend radius. The outer layer which are under tension should not be stretched too much, otherwise there is likelihood of being rupture. The amount of stretching depends upon the sheet thickness and the bend radius. Lower the bend radius, higher is the strain in this zone. Hence, there is minimum bend radius to be specified depending upon the material characteristics, that is the sheet thickness and the material used. As shown in figure aside, the outer fibrous material are in tension while the inner fiber are in compressions. Because of Poisson's ratio, width of part, that is bend length L, in outer region is smaller and in inner region is larger than the original width. So, in order to calculate the bend radius or minimum bend radius is radius at which the crack appears on the outer surface of the bend. It is given by a formula as R is equal to T into bracket 50 upon small r minus 1, where the capital R stands for the bend radius, T stands for the thickness of material, and R stands for the tensile reduction of area. To increase the bend ability of metals, increase the tensile reduction of area either by heating or by bending in a high pressure environment. The bend ability of a material depends upon: number one, tensile reduction of ductility of area ductility. As ductility of area ductility as increases, bendability increases. That is, as the R increases, the ability to bend of a material increases. The edge condition of the sheet, bend ability decreases as edge roughness increases. If the sheet is highly rough, the bending ability of sheet is low. The amount, shape and hardness of inclusion present in the sheet metal. The harder the sheet is, the less difficult to bend. Different material have different bend radius which are given in the different books and as per the sheet thickness available. Next is bending allowance. Bending allowance is nothing but length of neutral axis in bend and used to determine the length for a bent part. That is, the length of an bent part is nothing but the bending allowance. Bending allowance is given by LB is equal to A into R plus KT, where R is nothing but the bend radius, T is thickness, and K stands for an constant which is 0.33 for R is greater than 2 times thickness to 0.5 for R less than 2 times thickness. As the ratio of R and T decreases, tensile strain at outer fiber increases and the material cracks. Next point is bending direction. Grain orientation, as far as possible, the bending is to be done in a direction perpendicular to the grain direction in the metal. By virtue of the rolled sheets being used for bending, the grain direction usually is along the length axis, being in the direction of the rolling. That is, the sheet should be rolled as per the direction of the grains. There is possibility of cracks appearing at the time of bending if the bending is done along the grains or perpendicular to the grains as shown in figure. But if two bending are done on the same sheet at right angle, then it may be desirable to make them at 45 degree to the grain direction so that risk of cracking is minimized. So as far as possible, the bending should always be done in a direction perpendicular to the grain direction in the metal. That is, it should be along the direction of the grain direction. It should be along the grain of the material. Next point is spring back. During bending, the load is applied to bend the part in the expected shape. The bending tool bends metal into a certain angle with a given bent radius. After bending, when the tool is removed, there is dimensional change of the bent part as shown in figure aside. Widening the angle and increasing the radius is referred to the spring back effect. Spring back in bending is difficult to estimate theoretically, but it is essential to compensate it because the bend geometry gets affected by the spring back directly. According to the plastic deformation theory, the material is divided into two zones, the elastic zone and the plastic zone. The elastic property tries to maintain the material in the initial shape, whereas the plastic property tries to retain the material in deformed shape. In a sheet metal bending process, the bending load increases until material exceeds limit and enters the plastic deformation state. The outer surface of material is subjected to tensile which propagates inward towards the neutral plane. The inner surface of material is subjected to compressive stress and it propagates inward towards the neutral plane. This means that the metal near the neutral axis has been stressed to values below the elastic limit. This creates narrow elastic band on both sides of neutral axis. The metal far away from neutral axis may be stressed beyond the yield stress and has been plastically or permanently deformed. When bending load is removed at the end of bending stroke, the elastic band tries to return to its original condition but is restricted by plastic zone. When elastic and plastic zones reach equilibrium, it results in partial elastic recovery which is called as spring back. Thus, the workpiece tries to spring back and bent part slightly opens out. The factors affecting the spring back are many of them such as yield strength, Young's modulus, strain hardening exponent, strength coefficient, sheet metal geometry, thickness, width, tool dimensions, punch travel, punch velocity, etc. Spring back ratio. The amount of spring back can be defined by a non-dimensional spring back factor Ks, which is ratio between the final bending angle and the loading bending angle, or by spring back angle as Ks is equal to theta f upon theta I. Next is spring back angle. Angle and radius are intimately related to each other and hence spring back can be estimated approximately by the equation given. This equation has been used as a simplified reference for approximation of spring back assuming the thickness and arc length as constant. The equation is change delta t theta is equal to theta I minus theta f. Bend force. Bend force is the force required to cause a sheet metal to bend at an angle and form the desired shape. Bend force depends upon maximum external bending moment, which consists of two elements. First, the bending moment due to bend force and the punch travel. Second, additional moment to overcome the friction around the die shoulder. Bend force is influenced by sheet metal properties such as thickness, tensile strength, strength hardening, strength coefficient, tool parameters such as punch radius, die radius, process parameters such as punch displacement and bending angle. Bend force can be estimated by assuming the process as a simple beam bending. The maximum bend force P can be expressed as P is equal to K into mu sigma mu into L T square upon W, where P is nothing but the maximum bend force. K is equal to die opening factor, which usually ranges from 1.2 to 1.33. Sigma u is nothing but the ultimate tensile strength. L is equal to length of the bend. T is equal to thickness of the sheet or sheet thickness, and W is nothing but the die opening provided in the bending die. The last part of today's session, bending dies. The first bending dies type is roll bending. Roll bending is bending plates with a set of rollers as shown in figure below. Roll bending is similar to bending as the material is formed by applying the force. The sheet metal is not cut and no material is removed. For this reason, roll bending of the metal sheet is one of the cheapest sheet metal forming methods. Roll bending is used if metal sheet panel is to be given larger, smoother radius, which we can only produce in our press brake with step bending. Next is bending. Bending the periphery of sheet metal into cavity of die to improve appearance and eliminate exposed edges. As shown in figure, in this process, the edge of the sheet is bent into circular or counter shape of the die itself or formed into curl using one die or a pair of dies. Beading of the ends of sheet improves its stiffness and enhancing its moment of inertia at the edges. Third is flanging. Flanging dies or flanging. Flanging is bending edges of the sheet metal at 90 degree or at various angles as shown in figure. Bending the edges of sheets to 90 degree for improving their stiffness or for assembly is called flanging. If the angle of bend is less than 90 degree, it is called as flaring. Either compressive or tensile hoop stress is involved in flanging process. Flanging is a process of bending the edges of sheet metal at 90 degree. Flanges are created using flanging die that wipes the metal between punch and lower die section. Both tension and compression occur during flanging process. And the last is dimpling. Dimpling is punching a hole followed immediately by the flanging by flanging the edges. Flanges can also be made by combining piercing the sheet with a punch and followed by expansion of pierced edge using expander punch. This process is called as dimpling. Thank you. This is for today's session. In today's session, we have completed the different parameters of bending, such as bending radius, bending allowance, bending length, bending force, and different types of bending dies. Thank you.